Hey Marta, can you hear us?
Yes, hi.
Thank you for being here. It's a pleasure that you accept the invitation. Here in Mexico it's almost 12 p.m. And I think in Italy it's almost 7, right?
Yes, it's 7 here.
Well,
Yeah.
thank you for being here. It's an honor. And well, the main objective of this webinar is to involve more people here in Mexico in space architecture. But also we have a contest that that it'll be the next week will be the contest, and it's about space architecture thinking in the moon. So I was looking for somebody that has a lot of expertise in this kind of topics, and I found you. So thank you for being here. And well, it's I think it's time to start. So if you want to start, it will be an honor that you can start now. You can share your screen, and also we will be recording the meeting because we have some students that cannot access today, so they will be seeing the webinar for other time.
Okay, thank you so much. And thank you so much for the invitation, for having me here. I'm happy to be here with you all. Okay, I'm going to share my screen. Okay, can you see it?
For sure, we can see it.
Okay, so hi everyone. My name is Marta Rossi. I'm from Italy and I'm a PhD student at Politecnico di Torino. I've been studying space architecture for a few years now, and I'm also focusing my PhD research on space architecture. So today I want to introduce this exciting discipline that is space architecture. First of all, I would like to show you the official definition that we have of space architecture. This discipline has a kind of a long history. Architects and designers were involved in space programs since the beginning of space exploration. But the official definition, the official recognition of this discipline happened in 2002. And a few space architects around the world gathered, and they wrote down some principle of this discipline, and they came up with this definition, which is space architecture is the theory and practice of designing and building inhabited environments in outer space. But what do space architects actually do? So what do we have to look at when we design a habitat in space? First of all, what is maybe quite different from what architects do on Earth is that as space architects, we have to think about the mission. So we have to design a concept of operations that will give us an overview of what the mission will be, because our design should will be in put inside part of a mission. So we have to know the number of astronauts that will be there, the number of missions, what we need to do to actually build our settlement. So if we need multiple missions, like a first robotic mission, and then a human mission. So we need to set out this how the mission will unroll. Then we have to consider the environmental constraints, which I'm going to explore more in detail further into the presentation. So we are in some extreme environments. So we have to consider that when designing a space habitat. And we have also technical constraints, because we are in an environment which is not suitable to sustain human life. We need to consider high-tech solutions to design our habitat. Then we also have to take into consideration human factors. Uh, it's true that we have to ensure survivability for our astronauts or possible tourists in the future. But we also are designing for actual human beings. So it is really important to consider the psychological effects and also physiological effects that living in a space environment would uh, would entail. So we need to plan for that. We need to take into consideration that these astronauts will be in a confined environment for a lot of time, especially for those missions, those longer missions like for Mars. So we need to design with that in mind to provide astronauts with a comfortable space. And we also need to provide some spaces that can also counteract as for the physiological problems that can arise when staying in a microgravity or a reduced gravity environment. So, for example, in these kinds of environment, astronauts will experience muscle density loss. So we need to also provide some spaces to act against that. And all of these things are part of our habitat design. So we need to consider all of these elements to design our habitat and to bring together all the functions that are needed and that respect the many constraints that a space environment poses. And another important thing to consider is mock-up and testing. This is really important, and this is something that we architects on Earth maybe don't do or do it differently. Of course, it's a different process, but for space, we need to design the mock-up and to do a lot of testings. There's technology readiness levels that need to be met for the design to be actually usable for space missions. So I wanted to just mention some examples of what a space habitat has been and is nowadays. So we've already seen some examples of space architecture. First of all, the lunar module from the Apollo program in the 60s, 70s over the past century. This is the first and only for now planetary space habitat. It was designed for very short-term missions, so it was really a really small habitat with all of the functions that the astronauts needed to do in just one small space. So this will change in the next years, since we are going to further explore the moon with the Artemis program that for sure you know it's in progress. So other examples are the space stations like Salyut, Skylab, Mir, and the ISS. So here you can see a drawing made by a space architect, one of the first space architects. She's Galina Balashova, and I suggest you to look at her beautiful drawings. She did quite an inspirational work. She was studying a lot of things about the design of these habitats. She designed the interiors of Soyuz capsules, of the Salyut space station, and also of the Mir space station. And what you can see here is Mir space station. She conducted this study about the colors of the internal elements. And I think it's a quite interesting example of space architecture. So I suggest, if you can, grab her book, well, the book that was written about her, um, because it's really full of her drawings and really beautiful. So, what are the environments that we're designing for as space architects? First of all, of course, there's the moon, which is one of the well, the closest environment, space environment that we can design for is actually LEO, low Earth orbit. But our next objective in space exploration is, of course, the moon. And we have the Artemis program for that. So when we're designing for the moon, we have to consider a lot of different elements to actually provide a habitat that is livable and that can sustain human life. First of all, what is really important in space, what we have to consider when designing for both for Leo, for the moon, for Mars, is radiation. So in space, there's an environment that is highly dangerous for human life, especially on the moon and on Mars, because we are here on Earth. We are protected against radiation because we have our atmosphere, we have our magnetic field, and we are inside the Van Allen belts, which are these belts of these electromagnetic fields that protect the Earth. So when going to the moon and Mars, we're outside that sort of safe zone. And we have to deal with, especially with the galactic cosmic rays and solar particle events. So when designing a space habitat, we have to provide some kind of protection, of reduction of these doses of radiation to ensure survivability of human beings. And we also have here on the moon very thin and weak atmosphere, almost no atmosphere, and a very thin and weak magnetic field. So that is why we don't have this protection against radiation. So we have to keep that into consideration when designing a space habitat. We also have no surface pressure. And this is really important to keep in mind, since we have to provide pressured habitat to provide a habitat, a space that has one atmosphere, which is what we experience here on Earth. So inside the habitat, we should have a pressure of one atmosphere. And outside there's no pressure. So usually in space habitats we have airlocks to balance this difference in pressure. Another hazard that we that we have on the moon are micrometeorites. So we also have to shield our habitats against these possible impacts. And another important feature to consider that can also be something that can spark new ideas for our designs is the reduced gravity, which is not to be confused with microgravity, which is what we usually consider as zero gravity. So it's the state of weightlessness that astronauts experience on the ISS. So opposed to microgravity, there's reduced gravity. And on the moon, we have approximately 1/6 of terrestrial gravity. So this could be interesting to use for designing new solution of internal layout, because objects, furniture can be used in a different way when there's a different gravity level. So that is something to consider and maybe to use. And then lastly, there's temperature fluctuations. So we have these really high extremes, as you can see here, and this is important. It's really important to provide shielding against these temperature fluctuations, to provide a habitat that has an internal temperature that's similar to what we experience here. Then there's Mars, which is the planet that's more similar to Earth. But it's also quite distant from here. So it requires a travel of like 6 or 9 months. But it has some interesting features that can really be useful for a possible future settlement. So first of all, as I said, radiation is also a problem here. So we still have to deal with galactic cosmic rays and solar particle events. Mars also has a thin atmosphere, but it's a little bit thicker than the one we find on the moon. And it's mainly composed of carbon dioxide, nitrogen, and argon. Mars has no magnetic field, so the atmosphere is thicker, but since we don't have a magnetic field, this surface is still exposed to high levels of radiation. So shielding structure should be provided here too. Then another important feature of Mars is dust storms. So we have these really powerful winds that provoke some dust storms from now and then. So shielding is really important to provide some kind of protection against those. An interesting characteristic of Mars is that the day is actually really, really similar from our terrestrial day. So the terrestrial day is approximately 24 hours, and here is a little over 24 hours. So like also for the circadian rhythm would be, it could be interesting, interesting feature to ensure an environment that's really that's similar to what we experience here on Earth. The surface pressure here on Mars, there's some kind of surface pressure, but as you can see here, it's really, really low. So we still have to provide some kind of structures to provide this balance between the external non-existing pressure and the internal 1 atmosphere pressure. Then here there's also the hazard of micrometeorites, so we have to shield against them. The reduced gravity here is a little bit different from the one we find on the moon. So it's 1/3 g instead of 1/6. And temperature fluctuations are a little less extreme, but they're still they still have to be considered when designing a proper thermal insulation. Then we have low Earth orbit. This is the place we've been traveling for years now, and this will for sure be the place we will continue to travel. And right now it's expanding, and commercial space space companies are looking toward settling their structures here. So it's an interesting environment to explore and to consider for habitat design. Here we still have the problem of radiation, but it's really less problematic than the one we have both on the moon and Mars. So astronauts experience high levels of radiation when staying in orbit, but it's still less radiation dosage than the ones that they would experience on Mars and on the moon. So the altitude, as you can see here, and also from the drawing, is less than 1 kilometer. And we still have the micrometeoroids and also debris problem. So the habitats should have some kind of shielding against those, or some kind of maintenance to provide fixing when needed. And we're in a vacuum environment. So it's quite different from the one we find on the moon and Mars, but still we need airlocks to go outside. So same kind of problem with the pressure, different pressure levels. And as I was mentioning before, we're in a microgravity situation. So we experience weightlessness, which is kind of interesting from a design perspective, because we have a lot of different possibilities and different ways to use the internal environment. Here on Earth, we don't use, of course, the ceiling so much. We use our floor, we use the walls, but we don't use the whole room. In a microgravity environment, we can do that. We can use the whole room. So it gives some new ways of using internal space and some new ideas for designing internal environments. Here, temperature fluctuations still happen, of course, so thermal insulation is still needed. But of course, the most extreme temperature fluctuations, we find them on the moon, but still we need thermal insulation. So now I want to introduce this classification of 3 different types of habitats. In the space architecture world, there's this classification. So there's 3 different classes. Class 1 is the pre-integrated structures, class 2 is prefabricated, and class 3 are the ones produced in situ. So for the class 1, pre-integrated means that all of the structure is produced on Earth, then it's shipped into space, and it's ready to be used. It doesn't need to be deployed, but it's already made or already ready. An example of this is, of course, the lunar lander, which I'm sure you can recognize. But it's basically all of the habitats that we've seen since now are of class 1. So we have these rigid structures and these ready to be used habitats. Then we have class 2. These are prefabricated on Earth, but then they're shipped into space and they are deployed. So they need deployment to be actually used, to be ready. An example of this is the Transub, which is a NASA initiative. This was a project developed around the 2000. And these structures are mainly inflatable, so they're made of membranes which are packed when launched, and then they are inflated and they can be used when inflated, when pressurized. Class 3 habitats are produced in situ. This is the least achievable now, in my opinion, with the technologies that we have today. Mainly today we are exploring the a hybrid between class 2 and 3. So, for example, the use of regolith, which is the soil that we can find on the Moon and Mars, which, for clarification, regolith on the Moon and regolith on Mars are two different things. They're made of different elements, but the name is that is used to refer to the soil of Mars and the Moon. There, it's called regolith. So we can use regolith to 3D print a shield, a structure that can shield. And we can use an inflatable structure which is placed underneath this 3D printed membrane. So we can see some examples nowadays of these kinds of structures. But in the future, the goal is to bring less material as possible, less not many structures, not many things from Earth, because it's expensive to bring cargo from Earth to the Moon or to Mars, or of course to orbit in space in general. It's really expensive. So we need to decrease the economic costs, and to do so, if we use what we have already there, it's better. So we are working towards that. An example of this hybrid between class 3 and 2 is this project, Lunar Lantern, developed by Icon, which is a 3D printing company which develops 3D printed houses here on Earth. But they are also exploring 3D printed technologies on the Moon. So I suggest you to go see their projects. They're called Icon Build. They have really interesting projects also on Earth. So they, for this project, they have this 3D printed layer and a fabric liner, which is pressurized. So it's not completely made of in situ materials, but it uses a lot of materials that are found on the Moon. So this is an interesting use of the Moon resources. Inflatables are what's being explored nowadays for the future of space exploration. The traditional habitats are made mainly of aluminum or rigid materials, but now we are exploring these materials, textiles and membranes that are really light, that are and that provide a reduction of the costs of transportation. And moreover, another important feature of these inflatables is that since they occupy a small volume when packed, and they can be inflated and they expand, they can provide a bigger volume. Since what's important is that the cargo that's being shipped fits into the launch vector, and of course respect the the mass constraints. So what fits into the launch vector can be smaller than what the final habitat would be. So when it expands, it becomes bigger. And this is really crucial to design more spacious habitats, which is really important, mainly from a psychological side, because if astronauts have to be like on Mars, which would entail a longer mission, if they have to be there in a small cramped space for many months, with the same people and with very little space, very little privacy, that would be really challenging for them. So having a habitat that can provide a more internal livable space could be really beneficial to provide some countermeasures to the negative effects that they can experience. So this is another important thing to consider, and inflatables are actually really useful for to solve that problem. So their potential applications are both for orbital habitats and for planetary habitats. So we're really focusing on the moon with the Artemis program. So we're focusing on planetary habitats. I don't know if you've already seen some projects, but for example, there's the Moon Village developed by ESA, SOM, and MIT. And this project has many different inflatable habitats put together, and these compose the Moon Village. Many experts are exploring this technology for planetary habitats. But they could be really useful also for orbital habitats. And actually, an inflatable habitat has already been tested for orbital applications. This inflatable habitat that I'm referring to is called BEAM. It was developed by Bigelow Aerospace, and it's currently there on the ISS. So it's been deployed multiple times to ensure that the structure is stable, that can withstand multiple pressurizations and depressurizations. So it's been a real testing on the field of this technology, and it's been quite successful. The materials that we can use for these inflatables, as opposed to the traditional aluminum, are high-tech materials like Kevlar, Vectron, or Nomex. These are just some examples, just to give you an idea of what we can use for future space habitats. Maybe some of you already heard of some of these materials, maybe Kevlar, which is the textile that they use for bulletproof vests. So these are really high-tech textiles that can really withstand very high impacts, and they're really resistant. So their use in these kinds of structures has been proven to be successful and appropriate. Inflatables are not only used to design space habitats, but they also have been tested for other types of structures, of space structures, like this example of this inflatable antenna. This experiment was made into 1996, and it was successfully launched and deployed. So many different times this technology was proven to be useful for space applications. So right now I want to explore a little bit the Transhub, which I briefly mentioned before. So I just said that we have BEAM, the inflated habitat on the ISS, but this BEAM comes from the design of Transhub. So TransHub was a project, but it was actually tested. It passed a lot of different tests, but it never came to the actual building because of problems with funding. So the project was dropped. Later on, the patent was bought by Bigelow Aerospace, and they then developed the design, and they, of course, launched it, and it was successful, as I said. But I want to explore a little bit of what this project was. So it was designed for 6 crew members, and it had to be an ISS module, as it actually was at the end. And this is the volume, these 342 cubic meters, sorry. It was designed as a inflated shell attached to this hard central core. So I'm going to show you the plans so that you can see better what I'm talking about. So it has 4 different levels. So the first level that you can see here, you can see, I don't know if you, no, I don't know if you can see my mouse, but the pointer, but here, if you can see it, this is the central core. So this is the rigid part, and this one here is the inflated shell. So we have the design was based on the ISS racks, so it followed the same principle that the internal layout of the ISS has. And we have different functions covered into different floors. So like for the galley where astronauts would eat, with a window to look at Earth when they eat. Then we have here the crew quarters, and I want to point at an interesting feature, which is this wall here, the wall of the central rigid core, which you can see it's kind of light blue. And this is because they were planning on putting water into these walls. The reason why they wanted to put water inside these walls was to provide a better radiation protection for the astronauts when they were sleeping. So as you can see, there's 6 different crew quarters. So each astronaut would have had their private crew quarter, which is really nice. And then they would have this extra layer of protection, because they would spend many hours sleeping there. So many hours there would with an extra level of protection against radiation would mean that they would have less radiation absorbed. So this is an interesting way of providing protection. So water, ice is a strategy that you can also think for your projects. Then we have the 3rd floor with the area to exercise, and this is really important. As I said at the beginning, the astronauts experience some bone density loss, and also they lose muscles, the mass muscles. So they need to constantly exercise their muscles to counteract these negative effects of microgravity. So an exercise area is always needed, especially for microgravity, but of course also for reduced gravity, like on the Moon and Mars. And then the 4th level was just to connect the whole module with the ISS. So here you can see better what I was explaining. So there's the different levels, the central core, and you can also see the water wall in the middle. So now I want to show you one of my projects, just to give you another example. Um, so this is a conceptual project, and it's called DNA, Designing New Abodes. And I want to show you this project because I stressed the importance of shielding against radiation, and there's many different strategies to do so. So one strategy was the one that I just said. So using water or ice is a good idea to shield. Um, but there's also regolith, the one I was mentioning earlier, the 3D printed regolith. If we have a thick layer of regolith, and inside that we have our habitat, there's some kind of protection, of reduction of the level of radiation that the astronauts will experience. And it has to be really thick, at least 1.5 meters, if not higher than that, but at least 1.5, I would say. But another possible solution is using lava tubes. So there's lava tubes both on the moon and Mars. They've not been really explored and studied yet, so there's some problems there. But they are could be a viable option to provide radiation protection and protection in general from the external hazards. So this project was based inside a lava tube. First of all, it's on the moon, and the selection of the site fell into this lax mortis pit, which is connected to the lava tube. So the pit is the entrance of the lava tube. So we developed this concept with the idea that we wanted to bring the human element on the moon. So we wanted to bring some kind of significance with our project. We didn't want to just follow some technical requirements or environmental constraints, but we wanted to provide some kind of deeper meaning to our concept. So our idea, since we had this lava tube, which is really long and horizontal, so we had this horizontal configuration, we thought about the shape of DNA. To follow the shape of the lava tube and to bring the human element also from a conceptual standpoint. We developed a master plan, which is developed into different phases. So the DNA structure that we have inside the lava tube can be built over time. It does not have to be built in its entirety from the beginning, but we can bring to the moon just one loop at a time. So we have phase one, which has just one loop of the DNA structure that is connected to this structure on the surface, which is an observatory. And then we have the landing pad and the energy production zone, so the solar fields, the in situ resource utilization production zone, and the energy storage. So all of the infrastructure to provide the functioning to ensure the functioning of the settlement. And these all of these grows over time. So we have just one landing pad and just one small area of all the energy and ISRU areas. Then this grows and loops continue to be built. And we add another landing pad as the settlement gets bigger. Be sure to, if you in your project, if you also think of a master plan, so a possible expansion of your design, if you do so, a landing pad is absolutely needed. And it should be at least 1.5 kilometers away from your settlement for safety reasons. So be sure to include that into your designs if you explore a master plan. Okay, so the layout is like that. So you can see how the project is. So we have the observatories with two different airlocks, which can be entrance points. Then we have vertical connections, horizontal connections, and two streets that go along the lava tube. And then the DNA structure, which is secured to the walls of the lava tube with the cable structures. And as you can see here, there's all of the functions that we need inside a habitat, and they repeat with each loop, so that with just one loop, we have all that we need for a proper functioning of the settlement. As you can see here, you can see better how the settlement is, how all of the different elements interact with each other. And then lastly, I want to show you an impression of what the internal layout could be. So we tried also to make it a little bit fun. We introduced this slide, which is not, of course, just the only vertical element to connect the different floors, but we added this element just to play with the reduced gravity. And we provided this transparent wall. We have here the greenhouse and the transparent walls, so that the greenhouse where there's plants being grown, which must be in a controlled environment, they are separated from the other spaces, but they're visually connected to the other rooms, so that there's also positive effects from a psychological standpoint, so that humans can also have the interaction with nature that they don't have on the moon. So I think that's it. So yeah, thank you for listening. And if you have any questions, please ask.
Thank you so much, Marta. It was a really great presentation. I enjoyed it a lot, and you resolve a lot of dots that we have here in our team. So I just was wondering, maybe, well, in this time, I will say something in Spanish because I don't know if all the people can speak in English. Si tienen alguna duda, pueden dejarla en el chat mientras hacemos como una serie de preguntas de este lado. Igual no están abiertos sus micrófonos, pero si tuvieran una duda muy particular, podemos habilitarlos. Well, the question that I was thinking is, when we start traveling to the moon and when we have the habitats in the moon, we will have the radiation, as you said. But how you are planning to identify when the radiation enters to the habitat? Because sometimes maybe the habitat is going to be broken, or maybe the radiation is going to try to get inside. So if that happens, do you know how is planning to identify this kind of situations?
Well, radiation is basically always there. So the way you can kind of shield, because it's never an actual shield, but it's kind of a reduction of the dosage that you get. So if you have mass, you're kind of shielded. Let's say I will use shield just to be just because it's easier to talk about shields, but it's never uh, shields. We architects use the word shield, so use it, but it's just a clarification that it's always a reduction of the dosage. So if you have that kind of mass, you're safe. So or if you have well, there's also other ways that are being explored, um, like microalgae or mycelium. Those are other types of ways that are being explored that can shield against radiation. So basically, if you don't have that, you're not really shielded. So if you have a hole in your like if you have a 3D printed wall and you have a hole, that could be a way that radiation can get into your habitat. So that's the way you see if your habitat is safe or if it's not. So my suggestion is to keep the your if you have a shield, to keep it as without holes, without many holes. So just what you need to go outside, but not like big windows or something like that.
Okay, great suggestion. Thank you for that. I think we are having some problems with the chat because somebody said that he can write. Let me try
Oh,
to resolve this.
yes.
Mm, uh, uh, mm, Creo que hay una sección de preguntas y respuestas y ahí pueden, a ver, creo que ahí ya la habilité como una discusión y están preguntas, se pueden ahí comentar. Creo que sí se podría. Si no, igual si tienen alguna pregunta pueden levantar la mano y podemos intentar habilitar su micrófono. Just one moment, Marta, please.
What? Sorry.
Just one moment. We're trying
Yeah,
to
yeah,
set up this.
of course. But I'm following a little bit of what you're saying. I can
Okay,
understand Spanish a little bit. Okay.
here's the question.
Okay, what architectural innovations are being developed in space habitat design to facilitate medical diagnosis and treatments on long duration missions, considering limitations in equipment, specialized personnel, and microgravity conditions? So architectural innovations, maybe I wouldn't talk about architectural innovations. I think it's maybe another field, the one concerned related to medical. I think it's important to consider that, but yeah, maybe it's not actually developed by architects, the actual devices. But for sure, I know there's sensors and wearable devices that are being developed. I know that there is like this study that comes to mind right now at MIT Media Lab, if I'm not wrong. they are developing these wearable devices to ensure um, the yeah, to understand which treatment you need if you are sick. They It should be something like that. So if you are interested, you can maybe send me an email, and I can find the actual reference and show you what I'm talking about, because I think I have a book where there's this device. So if you want to explore that, please send me an email. Maybe I can write my email in the chat. Okay.
Sure, sure.
Okay.
I think it will be
Okay.
interesting thinking about how the architectures are thinking to create these new areas like hospitals in Moon and in the Mars, because I think the architectures have to be related with medicine perspective, because we will have some hospitals in the Moon. So maybe in the next years we will see how this is related.
Oh yeah, yeah, for sure. Yes, yes. Yeah, I was thinking more short term. So that's why I wasn't thinking about architectural solution right now. But of course, the with bigger settlement and with more people going there, for sure we will need actual medical facilities. Right now, I don't think we need them because we are just sending a few astronauts. Well, we haven't sent astronauts yet to the moon. Well, of course, in the 70s we did, but we're not doing it right now. We will. We have astronauts that are training right now to go to the moon. But yeah, when we in the future, for sure, we need to explore that. So there's another question. Do you have any ideas or perspectives on how medical problems or um oh, okay, so basically around the same uh um concept of the first question about the medical. So yeah, I think that in the future, well, maybe that could be a nice design exercise to think about what a future settlement when it will be further there will be already people staying there for longer periods. What a medical habitat, a medical structure could be on the moon or on Mars. Maybe on the moon it's more more short term in terms of feasibility. But yeah, there could be for sure. I think that technologies like VR or AR would be involved in this case for the moon, not Mars. For Mars, we will need other types of technologies because of there can't be real time interaction. But for the moon, it could be, and for sure for Leo, it could be interesting to incorporate these technologies. Oh, there's
Right.
someone
I think
writing.
somebody's writing. Yeah. So we can wait just
Yeah.
a couple seconds. Yeah, I think the same, because for the moon, I think VR and AR will be really useful for medical perspective, like it's been in the International Space Station. It's something similar, so I think it will be something similar in the moon. So that's if you want to be part of VR teams, it's time to be part of VR teams.
Yeah. Yeah, for sure.
I think Luis Alberto is writing a great question here.
Yes. um what happened with the waste produced? There is any project to solve this problem right now? I actually, yeah, I'm not, no, for sure there's projects. I'm not aware of projects right now or now. No, I don't have a specific project in mind for managing waste production. But some waste is recycled, already recycled on the ISS. So for sure it will be recycled. And I know that people are thinking about how the waste of greenhouses will be reused. So I know that people are thinking about this problem. Um, so yeah, basically recycling is key for this.
I think we have just two questions more in the Q&A section. So I will
Oh,
read one if you want, or
oh
you
yeah,
can read it,
I
or
can, I
okay.
didn't see them. Okay, do astronauts need to be secured to their beds while sleeping on the moon? No. No. There's less gravity, but there's gravity. So everything will not float. That happens in microgravity. So if you're on the ISS, you need to be secured to your bed. If you're on the moon, no. And do you have?
I think it's
Oh,
the
okay.
same
Yeah,
question.
they
Yeah.
are the same. Yeah.
Mhm. Well, I think we are on time. So thank you so much, Marta, for being here, for your talk, for your webinar, and for your experience here in Mexico. For us, is a really honor to have people like you, because we are trying to be part of this, and we don't have here some reference in Mexico. So uh, you are helping us a lot, and if I know that you are going to be part of the judge team. So thank you so much for that too, and I will send you the next week the projects that the students are doing here in our university. So I think it will be really great for us and for students. It will be a really great experience. The last year we made something similar. We made a contest too, and they present really great projects. But it was only in orbit. So this contest will be in the moon. So it will be something different, and I think it will be more exciting for us. So thank you for being here. I will send you some details for the next week and some information by LinkedIn. So thank you so much for being here.
Thank you. Thank you so much for having me. Thank you for listening, and thank you for the questions. And if you have any other questions, please send me an email, and I will reply. And good
For
luck
sure.
with your projects.
I
And
also will
I
be
look
send you a
forward.
message about the you said a name that I can remember, that was the architecture that designed the
Oh
structures of
yes.
the space international the space stations that you mentioned in the first
Yeah.
session. So I will,
Galina Balashova.
well, thank you. I will send you a text because
Yes. Yes. Of
you can
course.
write.
Yeah.
So I will send you to the students too. So thank you so much. Have a good night.
And have a good afternoon.
Bye bye.
Thank you. Bye.